In today's class, we're going to be talking about vector equations of lines in 3 dimensions. If you followed me so far, then this should not be such a big jump. Lines in 3 dimensions. We're talking about the line L in space somewhere. Well, if line L goes through point P, X, Y, Z, it was just like this before. We had R going to that point, and we had vector A going up to this point. But now we're in space. So we can say it's the same thing. R equals A plus lambda B. Well, our R now, from the point 0, 0, 0, our positional vector says go over X, up Y, and up Z to get to this point. So that's where this X, Y, and Z comes from. The position vector of some other point on this line from the origin 0, 0, 0 to another point, we'll call that some other point A, capital A, on our little graph here. And remember, this is in 3 dimensions. It looks like it's just in 2. Is x1, y1, z1. So this is a point somewhere on the line, x1, y1, z1, plus what we've got to go from this point to this point. How do we get there? We have to use a vector. We'll call it vector b, and its components are a, b, and c. Well, I don't want to use the whole vector. I just want to use a portion of it. The portion between point A and point P. That will be lambda, some proportion of a, b, and c. Well, if you've done that, we know that parametric form is simply x equals x1 plus lambda a, y equals y1 plus lambda b, and z equals z1 plus lambda c, which I've written right here. How do we go from parametric form to Cartesian form? Solve for lambda. Minus x1 divided by a. X minus x1 divided by a. Solve for lambda. Minus y1 divided by b. Y minus y1 divided by b. Solve for lambda. Z minus z1 divided by c. And you get this Cartesian form. Consider 2 lines, L1 and L2. We know R equals A lambda B. So for L1, R1 equals A1 plus lambda B, where this is a vector and that is a vector. This is a positional vector of some point on the line L, and this is a directional vector. It tells you how to go from A to some point P that's at the end of R. Same thing here, R2 equals A2 plus lambda B2, where B1 and B2 are your directional vectors. They don't start at 0, 0. Vector A starts at 0, 0, and vector R starts at 0, 0. But remember, vector B is your directional vector. Well, vector B then is x1i plus y1j plus z1k, and vector B2 is x2i plus y2j plus z2k. Now, if L1 is perpendicular to L2, then we know its dot product or scalar product can be defined as the magnitude of B1 times the magnitude of B2 times the cosine of the angle between them. But if they're perpendicular, the cosine is 90 degrees. What's the cosine of 90? It is 0. So B1 dot B2, or the dot product or the scalar product, will equal 0 for perpendicular lines. And we can conclude that x1 times x2 plus y1 times y2 plus z1 times z2 for perpendicular lines will equal 0 for perpendicular lines. This is a great test for perpendicular lines. Does x1 times x2 of your directional vector, does x1 times x2 plus y1 times y2 plus z1 times z2 equal 0? If it does, then the lines are perpendicular. We're still considering these 2 lines. Line 1 is R equals A plus lambda B. Line 2 is A plus lambda B. We've got subscript 1, 1, 1, subscript 2, 2, 2. Well, here, A, R, those are all positional vectors. They have their tail starting at 0, 0. B, remember, is a directional vector. It tells you how to get from point A to point P. Well, B is x1, y1, z1, and x2, y2, z2. If the lines are parallel, if line 1 is parallel to line 2, then this is the big jump. You have to remember, we talked about this in our introduction to what vectors are. If they're parallel, then they're going in the same direction, but that doesn't mean that they are the same size. If I have this vector and this vector, they are parallel, but if I call this one B1 and this one B2, well, then I'd have to take some sort of fraction of B2 to have it equal to B1. This is a true statement for vectors. If they're parallel, then B1 is equal to MB2, which implies that each of the components is also proportional with something that making them equal, this factor of m. So x1 equals mx2, y1 equals my2, z1 equals mz2. I'm just taking each of the components of the two vectors. Well, if that's the case, we can divide both sides by x2. We can divide both sides by y2. We can divide both sides by z2 and solve for m. And when we do, we get m equals x1 over x2, m equals y1 over m2, y1 over y2, and m equals z1 over z2. Well, if m is equal to all of those things, then all of those things are equal to each other. And so this is what you need to know for parallel lines. x1 over x2 is equal to y1 over y2 is equal to z1 over z2. And where are we getting that? They come from here, from the directional vectors of each of the lines, which is found right here. That's where you have to go to look to check if they are parallel or perpendicular. For perpendicular, remember, the dot product will equal 0.